All right, good afternoon. Just looking into, again, just the test for review handout pages I have provided. And again, we've been working with, for the past week, exponents and logarithms, and we have crossed over into the threshold of looking into equations involving exponents. And we first glanced at exponential equations that share a common base, and we looked at last time, okay, those equations that do not have a common base. And we have for the first part, okay, so for the group we have in numbers 20 through 24, and we have and it says to determine the value of x, okay, and again, just laying the foundation of what we have for exponential equations as well as logarithmic equations. So again, we have, like with the properties of logarithms, again we have a base A logarithm of a to the x is equal to x, and that's when you have an identity between the exponential and the logarithmic bases. And in situations where if you don't have an identity, okay, like in the case of the base A logarithm of m to the r, and again we can write the power of r as a coefficient, where we have r times the base A logarithm of m. And also we have, once again, we have with the change of base formula. Okay, so we got the base A logarithm of m can be written as a ratio of natural logarithms, or as a ratio of base 10 logarithms if you were to solve through using the calculator. Okay, and now for what we have in the case of number 20, okay, now we have in this one we're looking at the base 5, okay, raised to the x plus 2 degree, and that is set equal to 18. And so we have here okay, so you have 5 to the x plus 2 is equal to 18. And now again with this property, okay, notice I have the variable exponential expression on one side of the equation, so it can be to our advantage to go ahead and write the left hand side in terms of x plus 2. So I can take care of the exponential base 5 by taking the base 5 logarithm on both sides. So here we have the base 5 logarithm of 5 to the x plus 2 is equal to the base 5 logarithm of 18. And so we had the left hand side, okay, so this will be x plus 2. And again, we have, for now, we have equal to the base 5 logarithm of 18. And what we can do here is that, okay, it says here to round the answers, okay, to 3 decimal places if the decimal does not terminate. So we can apply the change of base formula either using natural or base 10 logarithms. So here we have a is at 5 and m is at 18, and I would just go with natural logarithms on this one. But again, base 10 logarithms will have the same overall effect. Okay, so we have in this one, okay, so we got x plus 2 again is equal to the natural logarithm of 18 over that of 5. And for the numbers here, okay, so we got 1.7958 among the first digits. And if I look at solving for x, so I'm going to take 2 away from both sides, and so taking the difference, it looks like we're going to have a negative amount for x, and to the nearest 2 decimal places this is going to be about a negative 0.204. Okay, and if you were to plug in, there'll be a little bit of an error just due to the rounding. But if I took negative 0.204, added to 2, and took 5 to that power resulting from the sum, that should come out very, very close to 18. Now, we have, in the case of number 21, now we still have, again, working with the exponential base 5. And here we have raised to the x minus 1 power. And we have is equal to 3. Okay, and again, we can eliminate the presence of the exponential base 5. And again, upon taking the base 5 logarithm on both sides, so you have a base 5 logarithm of 5 to the x minus 1, and we have is equal to the base 5 logarithm of 3. Okay, so I have here, to the left I have x minus 1 is equal to the base 5 logarithm of 3. And for the base 5 logarithm of 3, again, I can take either the ratio of natural logarithms or base 10 logarithms. And I'll just use base 10. Okay, so your m is at 3. And the a is going to be at 5. So you have the base 10 logarithm of 3 over that of 5. Okay, and so we have x minus 1 is going to be equal to, and we have, with this number, we have among the first digits, we have 0.6826. And in the follow through, if I add 1 to both sides and I round to the nearest 3 decimal places, okay, so we have for x, okay, that is going to be about 1.683. Alright, now for what we have in the case of number 22, okay, so we have the appearance of the variable x in exponential position occurring on both sides of the equation. And for this one, okay, for this setup, okay, now we've got 4 to the x plus 1. And we have is equal to 18 raised to the x minus 3. Okay, so for what we have in the lineup, okay, now if you have x on both sides of the equation in exponential position, okay, it's not going to be any advantage really of taking a logarithmic base if the base doesn't appear in the calculator to begin with. Okay, so in this situation, you can either apply natural or base 10 logarithms to both sides, and we'll go with LOG. Okay, so again, say ln or LOG on both sides. Okay, so have base 10 logarithm of 4 to the x plus 1. And we have is equal to the base 10 logarithm of 18 to the x minus 3. And so just looking at what we have here, okay, so we have with x plus 1 and x minus 3, again, we can convert these expressions into coefficients on the basis of the base a logarithm of m to the r is equal to r times the base a logarithm of m property. Okay, and so for what we have here, we can make these binomials again into binomial coefficients. Okay, so we have that x plus 1 and all of x plus 1 times the base 10 logarithm of 4 is equal to all of x minus 3 times the base 10 logarithm of 18, and looking at what we have and distributing. Okay, so we have both x and 1, we have multiplying the base 10 logarithm of 4. So you have x times the base 10 logarithm of 4 and we have plus the base 10 logarithm of 4, and we have is equal to x times the base 10 logarithm of 18 minus 3 times, okay, the base 10 logarithm of 18. And looking at what we have now, okay, so you have two expressions in x and two just as constants in the base 10 logarithms. So if we gather together our variable terms, okay, so I can join x times the base 10 logarithm of 4 with x times the base 10 logarithm of 18 by subtracting x times the base 10 logarithm of 18 on both sides. So I have the x terms on the left, and I'm going to go ahead and move the base 10 logarithm of 4 by subtracting. And so for what we're going to have here in the lineup, okay, so we have x times, okay, the base 10 logarithm of 4 minus x times, okay, the base 10 logarithm of 18. Again, we have equal to negative 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. Okay, so we have for the difference between the x terms, we can factor out x. And so we have x times the quantity of the base 10 logarithm of 4 minus the base 10 logarithm of 18. Again, we have equal to negative 3 times the base 10 log of 18 minus the base 10 logarithm of 4. And just setting things up here, I can just isolate the x upon division. Okay, so I have that x is equal to, and again we have negative 3 I'll do the calculator notation in just a moment. So I have negative 3 times the base 10 logarithm of 18 minus the base 10 logarithm of 4. Again, we have all over the base 10 logarithm of 4 minus the base 10 logarithm of 18. Okay, now if you were to enter into your calculator, okay, it's just one statement. Okay, so we have for the difference in the numerator, okay, I want to put these items in parentheses. And again, just a little bit of color coding to demonstrate how the grouping symbols are going to arrive. Okay, so you have in blue, got for the parentheses in blue, this will quantify the difference. And here I have minus 3 times, okay, the base 10 logarithm, and you'll have very likely parentheses to appear just enclosing the numerical attachments of each base 10 logarithmic term. Okay, and the parentheses sort of create a crowding effect. Okay, so again, we'll close out for the difference. And again, we have the operation of division. And once again, I'm going to enclose parentheses around the difference in the denominator. So I got the quantity. Okay, so I got the base 10 logarithm of 4 minus the base 10 logarithm of 18. So we have closing out for 18 and closing out, okay, for the difference in the denominator. Okay, and so we have in effect, okay, if I take to about the nearest 3 decimal places, to the nearest 3 decimal places. Now I've got like 6.6868, and to the nearest 3 places, okay, this would be about 6.687. All right, so this will be what we have here to the nearest 3 decimal places. Now, so this one was kind of a long problem, and in comparison to numbers 20 and 21, and it's because we had to do a lot of reconfiguring and combine x terms as opposed to having one x term readily available to work with. Now, for what we have in the case of number 23, and we have for this statement, okay, we have the natural logarithmic exponential base e, and we have for 23 we have e to the x plus 1 is equal to 14. Okay, so I have e to the x plus 1 is equal to 14. And for what we have in this particular case, all right, we got the variable expression x plus 1 on just the left hand side of the equation. So we're going to have with this one, okay, I can take base e logarithm on both sides here. Okay, so you got the base e logarithm of e to the x plus 1. So this will go to x plus 1. And for the base e logarithm of 14, guess what? A base e logarithm is already going to be a natural logarithm. So I'm just going to kind of restate this. Okay, so you have x plus 1 is equal to the natural logarithm of 14, and this is already in your calculator, so you don't have to do any kind of conversion. Okay, so we have in this one, so for the natural logarithm of 14, and with this one, okay, this would be a number, okay, over 2.6, okay, 2.639. And just looking at taking 1 away from both sides, and we have to the nearest 3 places, and it's going to follow that x is going to be about 1.639. So again, the exponential base from the start was base e, and taking the base e logarithms, okay, so automatically we have the left hand side is x plus 1, and right hand side is base e logarithm of 14, which is natural logarithm of 14, and that value you had right at hand without even having to do a change of base operation, because you don't have anything like you know, like a base 7 logarithm. You got one of the two with log and ln. So that value was already available. Okay, so you have x equal to 1.639, taking the result to the nearest 3 decimal places. Now, for what we have in the case of number 24, okay, so we have in this situation, now we've got e to the x minus 2 is equal to 3 raised to the x plus 1. And for what we have in this setup, again, we had that one. Let's see, that was e to the x minus 2 is equal to 3 to the x plus 1. Okay, and once again, if you don't have either exponential base from your calculator to appear, you are at liberty to use natural or base 10 logarithms. And now for this equation, now you could still use base 10 or natural logarithms, but it might save you like maybe part of a step anyway if I take a natural logarithm of both sides. And the reason for this is that I do have the base e to the left. Okay, but you can still apply base 10 logarithms. Okay, now for what I have on the left, okay, so you got the natural logarithm of e to the x minus 2, and we have is equal to the natural logarithm of 3 raised to the x plus 1 power and let me just sort of repeat something here. So you got the natural logarithm of e to the x minus 2. Again, ln is going to be a base e logarithm, and here we have that of e to the x minus 2. So that will go to x minus 2. So this left hand side, okay, we're going to have an x minus 2. Now to the right, okay, I don't have such a match between the exponential and logarithmic bases. So the power of x plus 1, I can write this as a binomial coefficient. We're going to have all of x plus 1 times the natural logarithm of 3. And looking at expanding, okay, so we have all of x plus 1 times the natural logarithm of 3. So we're going to have, for the terms, we're going to have x times the natural logarithm of 3. We have plus 1 times the natural logarithm of 3, which we have as ln of 3. And looking at what we have in the setup, okay, so if I combine the x terms together, okay, so I'll just move, I'll keep the x terms on the right, so I'm just going to move x times the natural logarithm of 3 by subtracting, and then I have, as for 2, I will undo the subtraction by adding 2 to both sides, and so to the left we're going to have x minus x times the natural logarithm of 3 is equal to the natural logarithm of 3. Then we have followed by the addition of 2. Okay, and getting nearer to solving for x. Okay, so we have for the difference of terms, we have a common factor with x. So I have times the quantity of 1 minus the natural logarithm of 3, and I have is equal to the natural logarithm of 3 followed by the addition of 2, and getting x by itself, okay, by dividing by 1 minus the natural logarithm of 3. So we'll have x equal to the natural logarithm of 3 plus 2, and we have all over 1 minus the natural logarithm of 3. And just putting this in terms, we have operating with the calculator. Okay, so you have for x, okay, so we have, again, quantifying the sum, so you have the natural logarithm of 3 followed by the addition of 2. So we're going to close out for the sum. We have with division, so we have a forward slash. We have division by 1 minus natural logarithm of 3. So again, close parentheses around the 3, and then close for the difference in the denominator. Okay. And so with what we have for this statement, and we have to about the nearest 3 decimal places. Okay, so x is going to come out to about negative 31.422. Okay, so right at negative 31.422. All right, now in the crossover, okay, to what we have with the test for study questions, and I say just from the first group to look into the first item, okay, and So we're going back to what we have with an exponential equation that shares a common base. And here we have 8 to the x plus 2 is equal to 4 raised to the 2x. So for what we have here, I'm going to mention something in just a moment. Okay, now for 8 to the x plus 2 is equal to 4 to the 2x. Okay, now we have a common base with the number 2. And for 8 and 4, in terms of base 2, now 8 is going to be 2 cubed. And for 8 to the x plus 2, this will be 2 cubed to the x plus 2. And for 4 to the 2x, 4 is 2 squared. So for 4 to the 2x, we have 2 squared to the 2x. And with the power property of exponents. Okay, so for 2 cubed raised to the x plus 2, so I have 2 to the 3 times all of x plus 2. So this is going to be 2 to the 3x plus 6. And we have is equal to 2 raised to the 4x. Now we have single base 2 terms on both sides. So yeah, 3x plus 6 is equal to 4x. And just putting the x terms together, so I have 4x by itself, and this can be joined with 3x upon subtracting that term. So we got that 6 is equal to x. So the missing value x is going to come out to 6. Okay, and I'm just going to mention something. This is not an orthodox approach by any stretch of the means, but say if something jumps at you, instead of like having a common base, okay, you can say, well, you got x on both sides of the equation, and I don't have logarithm base 8, and I don't have a base for logarithm. I'm just going to show you another way. Okay, now again, if it jumps out at you, I don't have a base 8 or a base 4 logarithm, but say just fresh off of working with other exercises with the variable on both sides of the equation, if you recall more quickly that you can use natural or base 10 logarithms, and for this equation you can. So if I take like the natural logarithm of both ends, and for what we have here now, for the x plus 2 as well as 2x, I can make these into coefficients. And if I were to distribute, okay, so I have x times the natural logarithm of 8, and I have plus 2 times the natural logarithm of 8 is equal to 2x times the natural logarithm of 4. Okay, and just taking what we have here, if you notice we have a couple of x terms where the x term on the right is by itself. And what I'll do here, okay, I'll just join this with x times the natural logarithm of 8. And so we have just in the follow through. Okay, so you have 2 times the natural logarithm of 8 and so I'm just going to shuffle the order here. Just have right side of the equation move to the left and vice versa. Okay, and if you notice between the terms, okay, we're still looking at solving for x, and if I factor out x, okay, so I have x times the quantity of 2 times the natural logarithm of 4 minus the natural logarithm of 8, and I have is equal to 2 times, okay, the natural logarithm of 8 and again just for x, okay, so you have 2 times the natural logarithm of 8, and we have all over 2 times the natural logarithm of 4 minus the natural logarithm of 8, and just for what we have in terms of, say, for calculator notation, okay, so we'll have 2 times the natural logarithm of 8, and we have divided by, okay, and we have parentheses around the difference from the denominator. Okay, so closing out for the natural logarithm of 8, and again closing out for the difference. Okay, and so just taking what we have now, and so you got 2 ln of 8 divided by, and again don't forget your extra parentheses around the difference. So you have 2 natural logarithm of 4 minus the natural logarithm of 8. And again, that still comes out to 6. Again, this approach not strongly recommended if you have a common base, because if you're cognizant of the common base that exists, okay, it was going to save you some steps. But this other approach, even though it has a feel of going around your elbow to get to your thumb, that approach still is going to work. All right, now for what we have in the case of the next items, okay, and we have regarding number 4, and we have in this particular set, okay, so you're looking at the change of a base, okay, where you're looking at evaluating. And so for what we have in the case of the base 3 logarithm of 24, okay, it says round to 3 decimal places if the decimal does not terminate. So you got a change of base formula here. So you got base 3 logarithm of 24. Now 24 is not, it is a multiple, but it is not an integer power of 3. So we're going to have here, say for number 4, okay, so we can say that we have, now use natural logarithms on this one, so you have the natural logarithm of 24 all over the natural logarithm of 3. And so for what we're going to have here, for the natural log of 24 over the natural log of 3, okay, and to about the nearest 3 decimal places, this is going to be right at 2.893. Okay, now for what we have in the case of the base 5 logarithm of e squared, okay, this is kind of a different item to deal with. Okay, now we have with the base 5 logarithm of e squared, and I tell you what, I'll just bring this on over. I'll show you a couple of ways of going about this. And we have with the base 5 log of e squared, Okay, so I have the base 5 logarithm of e squared, and I'll show you different ways of going about this. Now we don't have a match between the exponential and the logarithmic bases. However, okay, if I go with ln, okay, so again your a is going to be at 5, and for the m, this is going to be the e squared. So I can go with the natural logarithm of e squared over the natural logarithm of 5. Okay, and let's say if I were to just enter this in, and I'll show you where I'm coming from in this one. So you have like ln, you have of e to the second Okay, so if I were to enter what I have here, so you got the natural logarithm of e to the second, and you have divided by, okay, the natural logarithm of 5. Okay, so you have about a 1.243. I just wanted to mention something to you in case this might have appeared before you. We had the base 5 logarithm of e squared. Notice we had the natural logarithm of e squared over the natural logarithm of 5. And so, and one might say, well, isn't natural logarithm a base c logarithm? And the answer to that question is yes. Okay, so here we have a base c logarithm of e to the second okay, so natural logarithm, you have base c logarithm of e to the second, and this will go to 2 over the natural logarithm of 5, and that result still comes out to 1.243. Okay, so regardless of whichever approach you take, even with base 10 logarithm, I'll let this be this last alternate trial here. Okay, so if I have like base 10 logarithm of e squared over the base 10 logarithm of 5. Okay, so I got a base 10 logarithm of e to the second and we have all over the base 10 logarithm of 5, and you're still going to have the same reduction. Okay, so you have 1.243. Okay, all right. Now, for what we have in the case of number 6, and this was the base 6 logarithm of 216 and you could use the change of base formula, but 216 relative to 6, okay, you're looking at both multiples and integer powers. So for 216 is going to be 6 raised to the third. So base 6 logarithm of 6 to the third, okay, that is going to be equal to 3. Okay, but just if you went with the change of base route, we'll say that we have a at 6, m at 216. So if I have like the natural logarithm of 216 all over the natural logarithm of 6, and that's still going to come out to 3. Okay, so you're looking at different measures of scale, but it still comes down to the very same proportions, thus identical answers. All right, now for what we have in the case of the next item, okay, and we have with number 7, and we have with our items here, okay, so we have with 7, okay, so we're looking at writing expressions as sums and differences of logarithms. And for what we have in the case of numbers 7 and 8, so 7, okay, we have a base 3 logarithmic term, and 8, we have a logarithmic term in base 5. So what I'm going to do here is that for number 7, okay, so if I go ahead and write the radicals as exponents. Okay. So the rewrite for number 7, okay, so I have x squared times the square root of y plus 4. So this would be x squared times y plus 4 raised to the 1/2, and for the 4th root, a z plus 2 cubed. Okay, and so we're going to have here, okay, if you notice, you have exponent inside the radical, and the radical has the index number of 4, and so that is going to be the quantity z plus 2 raised to the 3/4. And so just looking at taking what we have in the rewrite and looking at expanding. Okay, so we have, so you have for number 7. Okay, so again, in expanding, multiplication implies adding, whereas division implies subtracting. And so we have, for the factors, we have 2 in the numerator, 1 in the denominator. So we now got the base 3 logarithm. Okay, we have of x squared. And next, okay, so if I work with y plus 4 to the 1/2, well, what was the square root of y plus 4? So we have plus the base 3 logarithm of the quantity of y plus 4 to the 1/2, and with z plus 2 to the 3/4 on the bottom. Okay, so that individual base 3 logarithmic term will be subtracted. Okay, and again, just converting, okay, the powers into coefficients. Okay, so again, the 2 is going from x squared, okay, that's going to be such that the base 3 logarithm of x squared will be expressed as 2 times the base 3 logarithm of x. And then we have next, okay, we have for the square root of y plus 4, which is y plus 4 to the 1/2, its base 3 logarithmic term can be expressed as 1/2 times the base 3 logarithm of the quantity of y plus 4. And we have minus, and converting the degree 3/4 to a coefficient. So we have minus 3/4 times the base 3 logarithm of the quantity z plus 2. And this will be one expanded notation for what we have. Okay, so we're going to have 2 terms that will be positive, and there'll be one where the only negative is going to be that which involves the expression in z. All right, and we have also in the mix, and we have with number 8. Okay, so we have here, we have the base 5 logarithm of 7t squared u to the third all over v to the fifth times z. And just looking at this in case I don't have any radicals to convert to exponents. Okay, so for here we have all the coefficients and degrees are in integer form. So here I have in the numerator I have 7t squared u to the third, and in the denominator I have v to the fifth times z. Okay, so here we have 3 factors in the numerator and 1 in the denominator. And looking at expanding, so we got the base 5 logarithm of 7 and I have plus the base 5 logarithm of t to the second plus, okay, the base 5 logarithm of u to the third, and then with v to the fifth and z on the bottom, okay, those respective terms are going to be subtracted. So I have minus the base 5 logarithm of v to the fifth, and I have minus the base 5 logarithm of z. And looking at converting from powers to coefficients. Now first of all, now some base logarithms of constants can be reduced, to integers, okay, or rational values. But for the base 5 logarithm of 7, 7 is not a multiple of 5, nor is it an integer power of 5. Okay, so in exact terms, we can keep the base 5 logarithm of 7 as it is. For the next term, okay, so I can write this as 2 times the base 5 logarithm of t, and I have plus 3 times, okay, the base 5 logarithm of u. Then I have next, okay, we have minus 5 times, okay, the base 5 logarithm of v, and finally I have minus the base 5 logarithm of z. And okay, so in terms of expanded form, it turns out that we will have 5 terms where we have 3 positives and 2 negatives. Right. Now, for what we have, just going back to exponential equations, and we have for numbers 11 through 13. Okay, so we have for number 11, okay, so you have kind of a basic problem with 2 to the x is equal to 3. And for what we have here, okay, again, we have x on one side, and so I can just knock out the 2 by applying base 2 logarithm of 2 to the x is equal to the base 2 logarithm of 3. Okay, so left hand side, okay, so the bases will cancel out, so we have x left over, and we have x equal to the base 2 logarithm of 3. And in the follow through, I can apply, say, the change of base formula. We have the natural logarithm of 3, if I go with ln, and have that with respect to the natural logarithm of 2. And if I take, let's see if it had number of decimal places, yeah, so it took 3 decimal places. So we have for the natural logarithm of 3 divided by the natural logarithm of 2. Okay, so that's going to be about a 1.585. and I'll mention this too. One might pose the question if you could take natural base 10 logarithms of both sides from the get-go, and the answer to that question is yes. So I'll just show you this one. If I took the natural logarithm of 2 to the x is equal to the natural logarithm of 3. Now if you notice, you're not going to have a match between the logarithmic and exponential bases, or exponential base. Okay, so ln is log base e, which is not going to be at 2. But for what we have here with 2 to the x, now the x, I can just write this as a variable coefficient. And guess what? If I isolate x, we have dividing by the natural logarithm of 2. So you have like the natural logarithm of 3 over the natural logarithm of 2. And guess what? This is where we were before. And through this pathway, you still come out to the same result in x, which you have right at 1.585. All right. Now for what we have in the case of the second item, okay, this time we have e to the x minus 2 is equal to 14. And in this one case, you have with e to the x minus 2 is equal to 14. Okay, and so we have here, okay, so we got the power in the variable x, okay, attached to the exponential base e. And guess what? I can just take, once again, the base e logarithm of e to the x minus 2 is equal to the base e logarithm of 14. So base e logarithm of e to the x minus 2, that becomes x minus 2. Okay, it's almost like, in a sense, almost like deja vu, okay, because you got like the base e logarithm of a constant, and that's just, again, going to be the natural logarithm of 14. Now for the natural log of 14, again, that is that 2.639 number. And following through by adding 2 to both sides. So it's going to turn out that for x, say when rounded to the nearest 3 decimal places, okay, that is going to be right at 4.639. Right. Now, in the case of number 13, this time we have the variable on both sides of the equation. Okay, whereupon we have 10 to the 3x plus 1 is equal to 12 to the x minus 1. And again, you can take either natural or base 10 logarithms on both sides. And we have, let's see if I can clean that up. So again, we have 10 to the 3x plus 1 equal to 12 to the x minus 1. And if I take base 10 logarithms, let's say on both sides, again, just for LOG, log is going to be base 10. Guess what? You got that of 10 to the 3x plus 1. So the left-hand side automatically becomes 3x plus 1. Now, you don't have a match between log in the base 10 and the exponential base 12. So for x minus 1, okay, we're going to make this expression into a binomial coefficient. Okay, so you have x minus 1. All of that times the base 10 logarithm of 12. Okay, so looking at what we have situated. Okay, so left-hand side, again, is going to be at 3x plus 1. And to the right, okay, so if I take x minus 1 and multiply by the base 10 logarithm of 12, so I'm going to have x times the base 10 logarithm of 12, and I have minus, okay, the base 10 logarithm of 12 Okay, so I have a couple of x terms. And I have a couple of terms that do not consist of the variable x. So I'm going to separate the pairs. Okay, so we have nx. I can just keep 3x on the left and just combine that with x times the base 10 logarithm of 12, okay, by subtracting that term from both sides. And we have moving the 1 over, so I can subtract 1 from the negative of the base 10 logarithm of 12. So we have in this situation, now we've got 3x minus x times, okay, the base 10 logarithm of 12 is equal to the negative of the base 10 logarithm of 12 minus 1. Okay, so again we have solving for x, and we have for this difference we can factor out x. So this will become x times the quantity of 3 minus the base 10 logarithm of 12 and we have minus the base 10 logarithm of 12 minus 1. And as we look at narrowing things down, okay, so we have for x, so x, again, you have the negative of the base 10 logarithm of 12 minus 1. And we have all over 3 minus the base 10 logarithm of 12. Okay, and just putting in calculator notation. So you have two differences, one in the numerator, the other in the denominator. So I'm just kind of doing a little bit of color coding here. So I got the quantity. They're going to have minus the base 10 logarithm of 12 minus 1. We got close parentheses. You have divided by, again, just adding the layer of parentheses, again, just to contain the subtraction in the denominator. So we have the difference between 3 and the base 10 logarithm of 12. So again, closing out for 12 and closing out for the difference between the terms in the denominator. So for what I'm going to have here, so I got minus, again, the base 10 logarithm of 12 minus 1, and we have divided by, again, all of 3 minus the base 10 logarithm of 12 and for this output, okay, so for x, okay, that's going to be about a negative 1.082. Okay, so again, these are samples of what we have with exponential equations, and we've been using logarithms to undo the presence of a lot of the exponential bases and to be able to arrive to the variable x. Now, and we have in terms of shifting gears a bit. Okay, so we're going from the realm of solving exponential equations to what will be logarithmic equations. And for what we have in the case of logarithmic equations, okay, and we got again just some of our fundamentals here. Again, we have that y is equal to the base a logarithm of x. And again, where we have that a is 0, greater than 0 with the exception of 1. Again, where x is greater than 0. And now, we've looked at, I mentioned this before, now when we first looked at properties of logarithms, okay, we had one variation of getting a logarithmic term to equal x. This was the base a logarithm of a to the x. And I had another expression. I said it will probably take a while before you see this again. And this is with, you had the other match between the exponential and logarithmic bases, where you have a to the base a logarithm of x, and this is also going to reduce to x. All right, now to show you why I'm putting all this up, and the reasons, okay, they'll become, I would say they will become rather apparent. Okay, once you're looking at a logarithmic equation, and say we have looking at solving for x, and we say that we have first of all, okay, for if you have, let's say, two terms in matching logarithmic bases. Okay, so if I have something like a base 2 logarithm of the quantity of 2x plus 3, and I have is equal to the base 2 logarithm of the quantity of x plus 14. Okay, now I'm just going to mention, okay, from this particular part here, from the first rule, okay, whatever I have attached, okay, so you have like both of these, you have base a is represented by base 2, and x you have respected by 2x plus 3 on the left and x plus 14 on the right. And it's going to mention, if you notice, you had the attachment must be positive, so I'm just going to write now whatever we have for x, both 2x plus 3 and x plus 14 must be positive. Okay, now both of these terms, they have the same logarithmic base, and so you can go ahead and set the attachments equal to each other. So here we're going to have 2x plus 3 is equal to x plus 14 so you've got a couple of x terms and a couple of constants, and we'll combine the x terms. So if I take x away from both sides, and I'll just move the constant 3 over by subtracting, and so you have that 2x minus x becomes x, And 14 minus 3 becomes 11. You can sort of double check here. So we got base 2 logarithmic terms, and I want the attachments to be positive values that will equal. So 2 times 11 is 22, plus 3 is 25. And guess what? 11 plus 14 is also 25. So the attachments are equal and both are positive. So we have 11 as the official value of x, okay, that will make this statement ring true. And let's say that if I have an equation, and we'll say that we have base 3 logarithm, just a term here with base 3 logarithm, and I'll have just this expression to consist of the variable x. Now we have the base 3 logarithm of x squared plus 3x is equal to the base 3 logarithm of 18. Okay, now for x squared plus 3x, whatever I have for x squared plus 3x must be positive. Okay, and both of these terms I have in base 3 logarithms, and I can go ahead and set the attachments equal to each other. So we have x squared plus 3x is equal to 18. So I have a quadratic equation in the setup, and what I can do is I can just write this in standard form. Whereupon I have x squared plus 3x minus 18 is equal to 0. And if I look at factoring, so we have the quantity of x plus 6 times that of x minus 3 is equal to 0. And for what we're going to have here, upon utilizing the zero product property, if x plus 6 is equal to 0, we have that x is equal to negative 6. And if x minus 3 is equal to 0, where we had the x is equal to 3. Okay, and I can check the results here. So negative 6, now the square of negative 6 is going to be a positive 36. 3 times negative 6 is minus 18. 36 minus 18 is a positive 18. So negative 6 checks out for 3. 3 squared is 9. 3 times 3 is 9. 9 plus 9 is 18. So 3 also checks out. So there will be 2 solutions that we have for x. Okay, and so we're going to have that x is equal to negative 6, and also we have positive 3 to work. So there will be 2 values that will work for x. Okay, now, and let's say that if we have where this particular property can come to the scene, and we'll say that we have a third situation here. Let's say if I have the base 2 logarithm of x is equal to 4. Okay, so whatever I have for x, whatever the attachment is, must be positive. In this case, we have x is the attachment, so that must be positive. Okay, so again, I have the base 2 logarithm of x is equal to 4. And if you notice, okay, from earlier with this last property, okay, so you had, again, a to the base a logarithm of x is equal to x. And guess what? We have the value of a is going to be at 2. So if I take this property, so if I make this into x, I can treat both sides as powers to which the base 2 is going to be raised. It's a little bit of a trick, okay, especially from a visual standpoint. So I'm going to undo the presence of base 2 logarithms by applying the exponential base 2. So both base 2 logarithm of x and 4 will be powers to which 2 is going to be raised. So you have 2 to the base 2 logarithm of x, that's going to go to x. And guess what? 2 to the 4th power, this will come out to the number 16. And so x is 16, that is positive, and it would ring true that the base 2 logarithm of 16 is equal to 4. Now say that for what we have as a remaining case, and we have say if I have a binomial expression for the attachment, I'll say that I have the base 3 logarithm of the quantity of x plus 5 is equal to 4. Okay. So we have the attachment in x, okay, at x plus 5. And again, that must be positive. Okay, so again, I have the base 3 logarithm of the quantity of x plus 5 is equal to 4. And just again, just undoing the presence of the base 3 logarithm. Again, I have this property again, a to the base a logarithm of the attachment is equal to the attachment. So with a at 3, so I'm going to say that we have 3 to the base 3 logarithm of the quantity of x plus 5 is going to be equal to 3 raised to the 4th power. Okay, so from the step before, okay, those sides will be powers to which 3 is going to be raised. So what I have on the left, okay, that is going to be x plus 5. And for what I have to the right, for 3 to the 4th, okay, that is equal to 81. And if x plus 5 is equal to 81, well, we're going to have that x is equal to 76. And 76 plus 5 is 81. And guess what? 81 is 3 to the 4th. And like your base 3 logarithm of 3 to the 4th, that is equal to 4. So that would check out upon examination.